So, couple of announcements. The second homework is going to be out tonight, sometime close to the midnight. We have to just do a few little things, but hopefully it's going to be out. So watch out for your second homework. As I mentioned before, the second homework will be, a fair amount of work. So my recommendation would be to start working on it sooner rather than later. The office hours for TAs handling the second assignment are going to be out. And so basically just, we've covered everything that you need to know to do the homework. So just basically start working on it, and particularly start working on the programming part. So if you're not familiar with OpenAI environment and, and such, you need to do a little bit of work. There's going to be a bonus question, and the bonus question is going to be a little bit more challenging question, where you would actually have to implement convolutional networks and such. So if you opt for it, go for it. You can get some extra credit. And it also would be useful for your final project, I believe. Many of you are going to be working on one way or another with some kind of data or vision data and such. So you'll be probably using that as well. Any questions? All right, how was homework 1? Easy? Yeah, so the second homework is probably going to be a little bit more involved than compared to the first one. So we'll make sure that you start doing your homework, your second homework. All right, so today we're going to talk about policy gradient methods, and let's see how far we'll go with the policy based reinforcement learning. There is a reading that you need to do basically from the homework, and so I would highly encourage you to go through the definitions because it requires a little bit of extra work to understand these methods. The basic idea is very simple, but at the same time, to go through the equations is a little bit, can be tough. Okay, so far, we've approximated the value or action value function using some parametric function, typically a neural network, parameterized by some parameters theta. Right, so we say the value function is a function of parameters theta. We're approximating the true value function, right, under some policy pi, or the same thing for the Q function, right? And then we would generate a policy directly from the value function, right? Once we have the Q function, once we have the optimal Q function, we can use, for example, epsilon greedy to derive a policy, right? Or can always take the maximum, take an action that maximizes your Q function, and basically take that action, right? So once you have Q function, you can derive the policy. So in this lecture, we're going to try to directly work with the policy pi, or have a parameterization of the policy so that we go and try to estimate directly the conditional probability of actions given the states and the parameters, okay? And in this class, again, we'll be focusing on model-free reinforcement learning. Okay, so just as we've done in all the previous classes. But that's basically going to be the goal for us. And that's why these are sometimes called policy-based reinforcement learning, because we're directly going after the policy, right? Sometimes I will also use this notation, just kind of being a little bit more consistent with this notation, which basically says, I really want to, estimate some probability distribution over actions conditioned on the current state, right? Because that's ultimately what you want, and given some parameters theta. Okay, so this is just a little bit of a kind of a comparison. So if we look at the value-based RL, right, we're learning some value function, right? And once we have the value function, then we have implicit policy, right? We can get the policy out of the value function. Policy-based methods, there is no value function. We're just trying to learn the policy directly, right? Just a mapping from states to the actions. And then there are sort of a class of algorithms called actor-critic algorithms, where we basically have both the learned value function and the learned policy. So the critic would be the policy, and the actor would be the policy, and the critic would be the value function, kind of evaluating how good this policy is, right? So these are kind of like a broad class of these different algorithms. Value-based, policy-based, and in the middle you have these actor-critic algorithms, which are probably the most dominant class of models that people use right now, right? Okay, so the advantages of policy-based methods, you basically sometimes you have better convergence properties. It can be effective in high-dimensional and continuous action spaces, and you can also learn stochastic policies, right? Because the policy that you can characterize could be the distribution of the possible actions that you need to take. So in principle, your policy could be stochastic. Some disadvantages, you know, sometimes these models, they would typically converge to some local rather than a global optimum. And then evaluating a policy can be inefficient. And we'll see some examples of that, and can have high variance. Let's look at one particular example. You know, you probably know this particular game, right? A rock, paper, scissors game. So you have two-player game, and scissors beat paper, rock beats scissors, and paper beats rock, right? So these are the rule of the games. Now, if you look at the policies for doing this iterative game, right? You take an action, and you look at the outcome. If you look at the deterministic policy can obviously be exploited. And we'll look at some examples of that, right? Particularly because you know the rules of the game. But the random policy is optimal. So when you're playing this game, the action that you're taking is always random, right? Between these three states. If you have some kind of deterministic policy that basically says, on the first try, I'm going to do scissors. Second try, I'm going to do rock. And third try, I'm going to do paper. This policy can be easily exploited by the other, by the opponent. All right. Here's another example. This is an example of a grid world. And let's say that in this particular setting, the agent cannot differentiate between the gray states. Right? So imagine that if you were in this location or in this location, you don't really know which one you're in. Okay? Think of, if you're in this location, you look here, you see the wall here. You're in this location, you see the wall here. Right? So from your perspective, these two locations look identical. And let's say, you can consider features of the form, like, is there like a wall to the north, then you move to the east or something like that. Right? So you can construct these kinds of features, and you can look at the value-based reinforcement learning. You can try to come up with some function, nonlinear function that takes these features, right? Is there a wall to the north? Then I'm taking a particular action. So you can try to figure out what's the optimal Q function is, or you can try using a policy-based RL and just try to parameterize directly the policy here, right? Again, these are the same features. You pass them through another function approximator, but you try to get the policy out directly. Obviously, I'm not telling you how we're training these models so far, but we'll get to that. Okay? Now, if you have an optimal deterministic policy, right, then in the gray states, like if you're in this state or in this state, you will always move to the west, or you always move to the east, because you don't know what state you're in, right? So if you're in one of those gray states, your only choices is go east or west, right? And if you have a deterministic policy, you always choose one action, go west, right? In this case, this particular policy can get stuck and never reach the money, right? If you start here, that's good, because you can go up and you can go down. But if you start here, you'll go here and go back and go here and you go back and go here, right? So this is just an example that it can potentially get stuck, a fully deterministic policy. The value-based reinforcement learning, for example, if you look at the greedy or if you look at the epsilon greedy policy, it can learn a near deterministic policy. which is okay, but at the same time, if your epsilon is small enough, it will kind of be stuck here for a very long time, right? You know, with some epsilon probability, you'll move here and then you reach the target, right? So the optimal stochastic policy here will be to randomly move east or west if you are in one of those gray states, right? So you might say you are in this location or in this location, basically move east with probability 0.5, move west with probability 0.5, and this will be the optimal stochastic policy for this particular example, right? And it will reach the goal state in just a few steps with high probability. Okay? So this is just an example of that, and policy-based reinforcement learning can learn this optimal stochastic policy directly. Okay? So we'll see some examples of that. But this is just one example for you to show that sometimes stochastic policies can be optimal. Now, let's look at what we're trying to do here. Just a little bit of a background. We're going to be given some policy pi with some parameters theta. Think of it as a neural network. You know, given some high-dimensional state, you pass it through the neural network and you spit out the action. Okay? You want to find the best parameters theta. But how do we measure the quality of a policy pi? Right? It's not clear because you know, you're still only getting sparse rewards. If you were getting rewards for every single action, that would be equivalent to supervised learning, right? Sometimes it's also called imitation learning, or if I tell you what the right action should be. So how can we do that? Well, in episodic environments where we run the simulation forward up until we reach some terminal state, we can use maybe this function, right? We can try to say, what's the value of that particular state? And I want to optimize this quantity, the theta, such that this is high, for example, right? That could be my objective. So if I'm in a particular state, I want to, you know, evaluate my policy by basically saying, if I look at the expected value of that state, what's the best policy for this expected value to be high, right? If you're looking at continuous environments, so these are not episodic environments, this is an agent that just continuously operates, right? Never reaches the terminal state and collects reward as you go along. You know, think about like, I don't know, what's a good example where, you know, you have, you're playing Quake and you basically never die, right? So this is like a continuous environment. There is no terminal state. So you can use the average, or you can use the average reward per time step. So what this is doing, if you think about this notation, d theta pi is a stationary distribution of the Markov-Chaffee on the policy pi, right? So this is basically saying that look at a particular state in my environment and average it with respect to the probability of being in that state, according to my Markov decision process, right? The more I spend time in the state, the more important it is. The less I spend time in the state, the less important it is, right? And if I average over all possible states, that's my objective, right? So I'm going to try to say, how do I change my policy so that this objective is maximized? Or you can also try to look at sometimes called average reward per time step, right? So you basically say, you know, look at the weighted average of all possible actions and the reward you get by being in a particular state, weighted by the probability of being in that state. So you think of D as the probability of being in a particular state, according to your Markov decision process on the policy pi. Okay? So these are all kind of like expectations, but if you think about in practice, what ends up happening is that you run your model for some time, right? You observe how many times you enter a particular state, and then you can compute these quantities, either these quantities or these quantities. Okay? We'll see some examples of how we can do approximations there. In many cases, we're going to be working with episodic environments where there is a terminal state. We run the episode, we reach the terminal state, and then we're basically going to be computing the expected value of the state. Okay? So, here again, we can use the average. In episodic case, this d function is defined to be the expected number of time steps, t, for which the state equals to that particular state. Okay? We'll look at the approximation. So think about tabular environments, so discrete environments. So you run your episode, you count how many times you visited a particular state. And so the expected number of time steps in which S is a randomly generated episode starting in S sub 0 and following pi and the dynamics of the Markov decision process, right? So again, it's just, you can think of it, what's the probability of being in a particular state? That's what the pi is measuring, right? And again, remember, the episode of experience under the policy pi is just you simulating it forward. You have a state, take an action, get the reward, you get a new state, action, reward, and you're sort of simulating it forward. So if you're counting how many times you're ending up in a particular state, normalizing it, that will give you the probability of being in that particular state. Okay, so intuitively that makes that should make sense, right? So if we can compute this quantity, right, the policy-based reinforcement learning is just an optimization problem. It basically says find theta that maximizes our objective, right? This objective. Now, this might be difficult to compute, right? Particularly if you have high-dimensional state space or if you are working with continuous state spaces. But in general, if I give you policy pi theta, I can compute this quantity, right? Because if I have a policy, I can evaluate, I can find the value function, I can take the average of all the states, and that's the evaluation metric. And then I'm going to say, how do I change my policy pi so that this objective is maximized, right? So some approaches to do that don't use gradient base is sometimes, hill climbing or genetic algorithms where you basically do some, in genetic algorithms, you basically do some random perturbations and try to see, is it improving or not? You can do finite differences and such. We are going to be looking at gradient-based optimization. So you can use gradient descent once you have the objective. You can use conjugate gradients or quasi-Newton methods. And we're going to be looking at the gradient descent algorithms. And there's a whole bunch of extensions, right? If you look at the literature, there is just so many different variations and different methods that go beyond gradient descent. So many expansions, and then there are also some methods that exploit sequential structure, right? Because it's a sequential process. Later on, we might look at some of those examples. So the policy gradient methods is really, you have the objective, which is your average value of average over all states. And the policy gradient algorithm is basically trying to find some local optimum of your objective J. And this is sort of, should be as no surprising to you. This is just standard gradient descent, right? You take the gradient, you basically, and you adjust your parameters by essentially doing gradient descent. This you can think of it as a policy gradient, you have a step size, and that's it. So this is your standard gradient descent, right? Okay? So if I go back again, just quickly, to emphasize, is that, again, given theta, if I give you the policy, I can compute this objective function, right? In practice, it might be difficult, but I can write this down explicitly, right? I sum over all the states, I look at the probability under my current Markov decision process, the probability of being in that state, I can compute the value of being in a particular state, and I take the average, right? The way you can get the intuition here is that, let's say some value of the state is really bad. Like being in a state that's near the cliff is really bad because you might fall off, right? But if you end, the probability of being in that state is very frequent, right? Out of all other states, like every time you execute the policy, your policy always wants to go to the edge of the cliff, let's say, right? If you have a policy that always wants to go to the edge of the cliff, then the states at the edge of the cliff are going to have high probability, but the value of those states are going to be very big negative. So your whole objective is going to be bad, basically. So you're trying to basically figure out how do you change the policy so that this quantity is as high as possible, right? Right? And if you have a policy that doesn't go to the bad states, or goes to the bad states very infrequently, so the probability this D here is very small, then it's okay, right? You want to make sure that according to your policy, states that you're visiting, on average, have high value function, right? So that's the objective. You're trying to find the policy such a way that, you know, the states that you're visiting, these states have high value function, right? So intuitively, it should make sense to you, right? Okay, so, and if we can compute this function, we can define it mathematically. We're going to look at the examples of how do we do approximations, obviously. But I can do gradient descent, and I can just optimize this objective, right? And I can find better policies so that according to my new policy, the states that I'm visiting have higher value function, right? Which is, again, related to the reward. So I want to find the policy in such a way that the states that I'm visiting have high value function, and at the end of the day, that basically means that my overall discounted future reward is high, right? That's what policy gradients objectives are trying to do. To evaluate the policy gradient, right, sometimes if you can't compute these quantities or you can't compute the derivatives, you could use finite differences method, okay? So, you know, you basically, for each dimension k, if you have n kind of degrees of freedom, you can estimate the partial derivative of objective with respect to the parameters. You're basically doing a small perturbation in the kth dimension, and you're just looking at estimating a gradient. So there are methods that do that, particularly if computing the derivatives is or could be expensive, or you can't do that. Right, so you can use n evaluations to compute the policy gradient in n dimension. Obviously, this is very inefficient, right? But sometimes can be very effective, right? It's almost like you're basically saying, if I take my parameters, I change one dimension of my parameters, would overall policy improve, right? Obviously, for large-scale problems, it's going to be very inefficient, but sometimes it can be effective because it's simple. Okay, and it works for arbitrary policies, even if the policy is not differentiable. When we think about the policy, we always think about I have some state, some image, or you know whatever that might be. I pass it through my neural network and I get some action. That would be a differentiable policy. But sometimes your policy might not be differentiable, right? You have a state and you have a bunch of logical rules of what it should be. Right? Or maybe something that's, you know, you have a black box simulator that runs inside your policy calculation. Something that you can't differentiate. In these cases, you can use these finite differences method because you don't need to compute the derivatives. You just need to basically compare two policies where you change your parameters or the input to the black box. Now, let's look at the policy gradient method and let's try to compute these gradients analytically. Okay? Now, we're going to make two assumptions, or one assumption. We're going to make an assumption that the policy is differentiable whenever it is non-zero. Okay? Think of it just basically saying, I want my policy to be differentiable. So we know the gradients of this quantity. Okay? Think of it as a neural network. You have some state, you have some differentiable mapping that maps states to actions, and you can compute the derivatives. Okay, so that's one assumption we have to make. And we're going to be using one trick. We're going to be using what's called the likelihood ratio test, or not the test, the likelihood ratio identity, where we're going to be using the following trick. If I look at the gradient of the policy, think of the policy as, again, the probability distribution defining space of actions conditioned on a state, right? Like a softmax or it could be a Gaussian if it's a continuous action. But there's some probability distribution. So what I can do is I can multiply and divide by pi. Okay, I have to make sure that I don't divide by 0, but let's say we don't. And then what I can do is I can rewrite it this way, right? Because this is just the definition of the gradient of the log of pi, right? So if I take the derivative with respect to policy, I can actually write it as the policy times the gradient of the log of the probability, log of the policy, right? And again, policies are always probabilities in this case. It's a probability of the action given the state, right? And this is sometimes known as the score function, right? And so now something interesting happens. Taking derivatives with respect to probability distributions is always a messy thing to do. But somehow taking derivatives of the log of the probability is much easier. Okay? This is the reason why people sometimes use log likelihood and not just a likelihood. You don't optimize likelihood function. You optimize log likelihood function, right? So there are certain things that will come around that we'll see which make it easier for us to deal with the logs as opposed to directly computing the probabilities. So let's look at the softmax policy. Let's say we're looking at the discrete actions, right, as a running example. And let's say that for now, we're going to be weighting actions using some linear combination of features. So let's say you come up with some features. You take the weighted average. You pass it through the softmax function. And you get the probability of taking an action. Okay? One way to think about these features is that, let's say, you can either construct those features yourself, or you can run a DNN, like a deep neural convolutional, with all the bells and whistles and skip connections here and trained in whatever fancy method you want to train, and then you get some features. You get your features at the top, you take a linear combination of those, and that's your softmax policy. That's essentially what you do anyways, right? I think folks in the computer vision, you just take ImageNet features and they stick logistic regression on top, and that's your classifier, basically, right? So let's say you have the probability of the action, right? Obviously, there is a nonlinear extension. You can just replace this phi with some deep neural network, and you can train your parameters and such. So that's not the point here. But you can also think here as a neural network with some softmax output probabilities, right? If you want to make connection to supervised learning, again, given the state, pass it through the model. If you have a discrete set of actions, it's a softmax probability distribution over possible actions. And this is just a neural network with softmax probabilities, output probabilities. So if I look at the score function here, if I take the derivatives with respect to parameters theta, I basically end up with this expression. These are my features minus the expectation of the same features under policy pi. Okay? Right? So for any of you who've taken like introductory machine learning class, this should look familiar. Right? This is like matching your empirical sufficient statistics to your expected sufficient statistics. Right? It's just a basic definition of taking the gradients of the softmax function. Okay? So that's the gradient. If this is matched, the gradient is 0. So now you take the derivative with respect to the log. Now let's look at the continuous spaces, right? This is discrete space. Let's look at the continuous action spaces. So suppose that you output not just discrete set of actions, but think of it as, I don't know, the velocity of your agent, how fast it should be going. You want to train a robot and you want to produce like how fast the robot should be going, right? Or maybe the degree of rotation. It's a continuous variable you want to predict. So in this case, you can just basically say, well, it's going to be the mean as a linear combination of state features, right? So you have some features as a state. You take the linear combination. The output is a real valued number. And again, you can have a nonlinear extension. You can replace this feature by some DNN with some trainable parameters. Okay? typically, for continuous controls, you have an input, you pass it through some nonlinear model, and you're getting out just some real valued number, right? Basically, you just don't pass it through softmax. That's what happens. Forget about the softmax. You just have the single output. And the variance may be fixed, or it can also be parameterized, right? So the policy could be a Gaussian distribution, which is commonly used, probably most commonly used as a Gaussian distribution, with mean given some function of the state. That's your prediction, how fast you should be going, let's say, and some variance, right, to characterize uncertainty. So now you have a probability distribution. And obviously, this variance can also be parameterized by the state, if you want to make it a bit more interesting. In many cases, just the variance is a hyperparameter that's fixed, right? So it tells you something about real valued action. In this case, you can compute the score function. So in this case, you can say the derivative of the log of pi, this thing, is just going to be your action minus its mean multiplied by the features, right? And divide by variance. Right? And under Gaussian, you should always remember, what is the Gaussian? Gaussian is always e to the negative something squared, right? If you see somewhere e to the negative something squared, think Gaussian. And if you take the log of it, right, something nice happens. You just have something squared, right? So if you take a derivative of it, you basically get this. So that's why in many cases when we work with a log or with a score function, a lot of things become easy. Right? Imagine taking derivative of something which is e to the something. Right? You have e to the something, and then you take the derivative, it's just going to be a big messy thing. But if you take the derivative of the log, it becomes, you have a very simple sort of representation here. Okay, any questions? So far, if we have these policies both discrete and continuous, we look at the log, we can take the derivatives. Okay? So now let's look at the one-step MDP. Let's look at a very simple class of Markov decision processes. Let's say we start at some state S, right? Some prior distribution, or some, like the probability according to your policy, you start at some states more frequently than others, and you terminate after one step with some reward. Okay? So let's look at this objective. Because it's a one-step MDP, you basically do one step, and in one step you just get the reward, right? So you look at this particular objective. So you want to find the policy in such a way that this one-step MDP, this objective is as high as possible. This objective is basically saying, take an expectation over all states and actions, right? An expectation with respect to pi. So it's a probability of state given action. This is probability, it's probability of action given state. This is probability of the action, and this is the reward. So this is just the expected one-step MDP reward, right? This is just writing down the expectation, right? You can think of it as just, this is modeling probability of state, this is modeling probability of the action given the state, and this is the reward. So you're just looking at the expected reward. If it makes it a little bit easier for you to think, how would you approximate this? Simulate millions of examples. Get in the state, you get the new state, you get the reward. Get the new state, state reward. And you just take the average. That would be what this function is, right? I'm just writing it down in terms of expectations. So what's the intuition, right? And that's exactly what I was saying. Under the MDP, the expected reward, one-step MDP, is you sum over all states, you sum over all actions, and you have this quantity, probability of state and action, the joint probability, right? And I can basically write it down as the probability of the state under my Markov decision process, probability of the action given the state, and the reward, right? So if under my Markov decision process, again, I end up being always in some states that have bad rewards, probable, then it's bad. you want to be in the states, or the states that are probable, you want them to have high reward. And obviously you want to choose the policy that takes an action that gives you the high reward, right? So you want to be in a good state and you want to take an action that gives you high reward, right? This is just the definition of the expectation. Okay? And this is exactly what's being displayed here. I can say it's the average of this quantity, like take the average of the rewards according to your policy, weighted by the policy, and average over all possible states. Right? That's the objective. Okay? So I can't really say, is it confusing or is it so obvious that I'm spending too much time on it? But nonetheless, so let's look at that. And now let's look at the likelihood ratio, use likelihood ratio to compute the policy gradient. Okay? So what's happening here? Oh. What's happening here is that I'm replacing this quantity, the gradient of this guy, I'm replacing with this, right? So if I take the gradient with respect to this objective, instead of taking the gradient with respect to pi, I'm going to be taking the gradient with respect to this quantity, log of pi. And you can obviously see that if I take the gradient of the log, what's the gradient of the log? It's 1 over pi times the gradient of the pi. And 1 over pi and pi cancels out, and so you have the gradient of this guy. Right? But now I can write it in this format. Right? I can say it's an expectation of the gradient of the log of the policy times the reward. Right? Right? Because if I just take the expectations, that's what I'm getting. Okay? Now, if I look at this, this is just one-step MDP. There is an extension of this is the policy gradient theorem that basically generalizes this likelihood ratio to multi-step MDP, right? Because you never terminate in one step. You terminate in like T steps. And essentially, the only difference is that you're basically replacing immediate reward with some long-term reward value, the Q function, right? Because the Q function is just basically telling you what's the expected discounted reward. So instead of getting immediate reward, you're replacing your immediate reward with a Q function. And so the policy gradient applies at the start of applies to start state objective, average reward, and average value objective. So there's a bunch of different objectives you can do. But for any differentiable policy pi, the policy gradient basically has this form. Okay? So the gradient of your objective here is the expectation under your policy. Take the gradient of the log of the policy weighted by the Q function. Okay? If I look at this expression, and just go back here, it's exactly the same as what I'm seeing here, except for this immediate reward is replaced by the Q function. Right? And remember what the Q function is. Q function is, expected discounted future rewards, right? So going from one step to multi-step, you're just basically replacing immediate reward with this Q function. Now notice that this Q function is a function of pi, right? So you kind of have to be able to compute this. So this is inequality. There's no approximations here. Okay? And then there is a whole bunch of extensions for this particular equation of what goes in here. Okay? And we'll see kind of different algorithms and such kind of use different approximations to this expectation. So in principle, you can update parameters by using stochastic gradient descent because I can compute the gradient. Right? Now, I can also do the following. Instead of computing this expectation, what I can do is I can use my return as an unbiased sample of Q. Right? I can use Monte Carlo strategy to get a sample from Q and just do this update. Right? Because I don't know what this thing is. It's difficult to compute. But I can sample, right? I can do multiple samples and try to estimate what the Q function is. So this is exactly by doing a Monte Carlo policy gradient method. It's an episodic, so you run the episode. In the Monte Carlo policy gradient method, let's look at the actual, and this is something that's also called reinforce. It's a fairly famous algorithm that, I'm sure many of you, if you haven't seen the definition of the algorithm, I'm sure you've seen people throwing reinforce left and right. It's like, oh, I'm going to use reinforce to do X, I'm going to do reinforce to do that. Right? And that's actually what the algorithm does. Your input is some differentiable policy, right? Some distribution of actions given the state parameterized by theta. A, some action space, some state. Initial policy, you initialize policy weight stated, like some random numbers. And then you basically repeat forever, right? You basically say you generate the episode, you start at some random state, you go all the way, following policy pi. And then for each step of the episode, you look at the return from step t, and you update the model parameters. Right? By looking at this thing. So this also has kind of sort of like an intuitive interpretation, right? If you look at this update equation, it's basically telling you, take the gradient with respect to the log of the policy weighted by the return. Right? You have big return. You basically want to move, you're going to have a big gradient by basically saying, I want to take these actions. Right? If you have negative return, then you're basically saying, unlearn my policy, don't take this action. Right? That's effectively what this equation is telling you and what this update is telling you. Big positive return, you're basically saying, yes, make this more probable because you're moving in the direction of taking this action. Whatever this action is, right? Because it will lead to a better return versus having a small return or a negative return. Okay? Any questions? This is kind of like a very well-known, very simple to use algorithm, right? Because you can just run the simulation forward up until some terminal state and just do the updates. You can compute this quantity. You can estimate this thing, and it's an unbiased estimator, which means an expectation you're doing things correctly. But it's also expensive because you have to run things forward all the way up until you finish, or up until you get your overall return. Yes, there's a question?
Does the PS depend on your pi theta?
Yes. Sorry, it should be dependent on pi theta. Because think of it as like it's a Markov decision process, so it's a probability of being in a particular state. So think of it, you have a policy. You run your policy, infinite number of times, let's say, right? You're running your policy infinitely long. And then that gives you the probability of being in each one of the states, right? So again, if your policy wants to be near the edge of the cliff, then the probability of those states will go up, right? It's a bad policy. So let's analyze the update. This particular update of reinforce. And let's rewrite it as follows. It's the gradient of the policy divided by the policy, right? That's the gradient of the log. So update is proportional to the product of the return, right? This is what you're doing. And the gradient of the probability of taking the action, actually taking, divided by probability of taking this action. Right? Let's see. So, what does this say? This basically says move most in the direction that favor actions that basically give you highest return. That's exactly what this term is saying. Right? This case, the update is inversely proportional to the action probabilities. So actions that are selected frequently are at an advantage. The updates will be more often in their direction, right? So what that basically means that if I take a probability of a particular action and that probability is really small, but I get a huge reward from it, then I basically, even make it more probable, right? If I take a particular action and it's very frequent, I always take this action. Even if I get a big return, it's still inversely proportional to that, right? So it doesn't matter that much. So you kind of like have these two pieces moving together. And again, at the high level, the most important thing is this guy here. All right, you're just trying to take actions that lead you to the more frequent, to the highest return. This is just weighted by the probability of the actions. So infrequent actions are kind of more important than frequent ones, right? Particularly if those infrequent actions lead you to good results. It's like, I don't know, how many of you heard about convolutional neural networks for ImageNet? For like ImageNet competition. How many of you have heard about like those kinds of models? Many of you, right? I mean, it's like if you've ever done with vision in any way, you know that models like ResNet or GoogleNet are, work really well. And then there's another model, I think I mentioned it before, called VGG, which was OxfordNet, that works remarkably well. And it's almost like the probability of things that they've done just don't make any sense, right? They basically did convolutions, like 3x3 convolutions on this huge image, which just a priori didn't make any sense, right? So your probability of trying on a 250 by 250 image, trying to like a 3x3 or 2x2 convolution, people just said that just improbable, right? But it worked remarkably well. So it's like one of those things that if it's improbable, but it works remarkably well, you kind of like want to explore more in that direction, right? So that's the way to think about this. So here's another example of a setting. So here's, you have continuous actions. You basically want to hit the small puck, a small force on puck. Puck is rewarded for getting close to the target. So the closer you are to the target, the more reward you get. And then the target location is reset every 30 seconds. And this is the policy that's trained using reinforce. Okay? So it's exactly the same thing. You just run it forward, and this is what it looks like. And this is the average reward, and then you basically like, your reward sort of improves, and obviously you have to, you have to do a lot of iterations. So reinforce-like algorithms, they have high variance. They're very simple, but they do have high variance, which basically means that you need to run a lot of simulations, right? Okay, let's see how we're doing on time. Yep. So let's look at the actor-critic algorithm. So let's look at these classes of algorithms. Okay. So Monte Carlo policy gradients, these reinforced type of algorithms, typically you have high variance. So they are very unreliable in practice. But what we can do is we can use a critic to estimate the action value function. Okay? So let's say we have another network which basically estimates the Q function, parameterized by some parameter theta. Think of it as, again, as some deep neural network that's approximating the true Q function. Okay? So the actor-critic algorithms, they maintain two sets of parameters. You have critic updates, which is the action value function parameter W, which is the critic. And you have an actor updates, which is the policy parameter theta, in the direction suggested by the critic. Right? So here's what the approximation. So actor-critic algorithm, they basically follow approximate policy gradient method, right? They're basically saying, find me the policy, but you're moving it in the direction of this quantity, right? So let's connect it back to reinforced algorithm. What is the reinforced algorithm doing? Reinforced algorithm basically says, run it all the way up until some terminal state and estimate what the reward is, right? Overall reward. This is basically saying, you know what? I'm going to get another network to estimate for me what that reward is. So I don't need to run it all the way to the end, right? It's like, on your homework, when you're struggling on your homework, you're basically saying, what should I do? You come to the TA, and the TA kind of like gives you some suggestions, right? You don't have to go all the way of writing your homework, submitting it, and getting like bad grade. And you say, okay, let's redo the whole thing, right? So you're basically getting another network that's giving you estimate of what the actual reward is, or what the actual Q function is, right? Does that make sense? And if you take the gradients of this quantity, obviously this is now inequality. The reason why it's inequality is because you don't know the true value of the Q function. If you knew the true value of the Q function, then that would be equality, and then things are easy. So you always come back to this question of, your target or is your own estimate, basically. But now you can take the gradients with respect to the parameters, this quantity. Now, obviously, you also need to update this guy as well, right? Because initially, your Q function is going to be random, right? You don't know what's a good state, what's a bad state, what's a good action, bad action. So initially, both of them are random, and so you're kind of looking at the objective to improve both of them, right? So let's look back just to make a connection. This is the policy gradient method. This is what the acticritic does. And you can see the approximation really comes in the form of this approximation, because you don't know what this quantity is. You can use reinforce to get an unbiased estimate of this quantity, right? You just run forward and see what ends up happening. Or you can use another network to estimate it for you, right? So how does it work? Well, the critic is solving a policy evaluation problem, right? So the critic here, this guy, is solving this problem. And we've kind of looked at this problem before, right? Remember initial few lectures. If I give you the policy, can you give me the Q function? Can you evaluate this policy by constructing a Q function? That's essentially what the critic is doing, right? And then how good is the policy for the current parameters? Well, this problem was explored either using Monte Carlo, which gives you, again, the reinforced algorithm, or temporal difference learning, right? Or maybe we can use we can also use least square policy evaluation, right? If we're working with linear systems. So how do we do? Well, let's look at the linear function approximation for now. So what we're going to do is we're going to update the critic parameters, W, by looking at the TD learning, in this case linear TD learning, and then we're going to be updating active parameters, theta, by policy gradient, right? And this is what the overall algorithm looks like. Let's see, you initialize some state, you sample some action. Again, initially it's just a random policy, so your action's basically going to be random. You sample the reward, you sample the transitions according to your Markov decision process. You sample an action according to your policy, and then you update, you do Q learning, basically, right? You update your parameters. You take the gradients, you estimate the policy gradient by, using this as your target. And then you update the parameters of the Q function, and you update the parameters, I guess, and you update the parameters of the theta. Right, so here's the update for the theta, here's the update for the parameters of the Q function. So you're kind of doing both, right? You're doing Q learning, at the same time you're also learning the policy. Right? This is TD learning. If you gave me a good Q function already, like if somehow magically there was another process, I give it a policy, and this process gives me a good Q function, then I wouldn't need to do these updates. I would just follow this equation. right? If somebody would always give me a good Q function, right? But because policy is changing, your Q function will change. And so now these kinds of coupling between the parameters theta and W. Your policy becomes better, your Q function changes, and then again, you're updating your policy, and then you're updating your Q function and such. So that's why you have updating both actor and critic. Right? Yes? They're not unbiased anymore. Yes. That becomes a bit of a problem because of the stability issues and such. Yes, indeed. Because now, if I look at, just if I go back here, if I look at this update, because I'm replacing it with something different, this is not an unbiased estimator of this, right? So yes, you can basically screw up. With reinforce, it's an unbiased estimate, so that's nice. But the variance is high because with reinforce, you're running your simulation forward. There's so many random decisions you're making, right? So you made a bunch of random decisions, you get big negative reward. You say, whoa, this is bad. But you maybe made some other random decisions and you would have gotten good reward, right? So it's an unbiased, but it has high variance. These kinds of models, just like as we've seen with TD learning, they have smaller variance, but they're biased, okay? Okay, now, there is one last thing that I wanted to mention is reducing the variance of actor-critic algorithms. And this actually leads to a whole bunch of classes of algorithms. What we can do is we can subtract the baseline function from the policy gradient, right? And this can reduce the variance without changing the expectation. That's a key. So let's look at this quantity. Let's look at this expression here, okay? It's the gradient with respect to the log of the policy plus some function of the state. Call it B of S. Okay? I can write down this expectation in this form, right? And something interesting happens. This term here doesn't depend on the action, right? It's just a function of the state. So I can pull this B out of here, right? It doesn't depend on the state. What's the gradient of this quantity? It's 0. Can anybody tell me why it's 0? Exactly. So if you look at this sum, these probabilities sum to 1. So this quantity is always 1. The gradient of 1 is always 0. Okay? So now, this equals to 1, and this function of the state, but not an action. That's important. Your baseline is a function of the state, but not of the action. Right? So what does that mean? That basically means that what I can do is I can basically add or subtract this quantity from my policy gradient algorithm. Okay? So for example, a good baseline is the state value function. Right? The state value function doesn't depend on the action. But what I can do, let's see if I can, yeah, so this is state value function, right? And so what I can do is I can basically say, well, this quantity is 0. If I set the baseline to be the value of the state, I can rewrite the policy gradient using the advantage function. And we've seen the advantage function before, right? It's the Q minus the value of the state. Right? And now, what I can do is I can basically rewrite the policy gradient theorem as replacing this Q function with an advantage function. Right? This is still an equality. Right? Precisely because this quantity is 0. So if I plug this in here, take an expectation, the expectation with respect to this guy of the policy gradient expression here is 0. Okay? So now I get basically the exact same policy gradient method. And it turns out that this particular trick reduces the variance of the gradient estimator significantly. It's almost like normalizing the gradients. Because sometimes you end up in a good state, sometimes you end up in a bad state, and you have, it's just there's no normalization. This particular expression gives you a very specific normalization. Now, how do you compute this thing? There is a whole bunch of papers, but in principle, you can train another neural network to predict this value. So you end up having 3 models. One is predicting Q, one is predicting V, the other one is doing policy, right? So kind of like managing all of these things at the same time, trying to decorrelate as much as possible. Okay, so next class, we're going to continue looking at the policy gradients, and we're going to look at, I think that in particular, we're going to look at different extensions of this model. Okay, so the second assignment is out today, so start working on it.